So in this video, we're going to talk about how to draw what's called the orbital diagram or orbital box notation for a particular element. In the previous video, we talked about how to write the spectroscopic notation or the electron configuration for a particular element. The 1s2, 2s2, 2p6, that notation. Now we're going to talk about how to do so that was the address. Now we're going to talk about how to draw the map or how to do this orbital box notation. Orbital box notations or orbital diagrams can be really helpful when explaining certain properties of atoms, particularly with regards to magnetic properties and also with regards to hybrid orbitals. You don't have to get scared yet, but hybrid orbitals is a concept that we will talk about in the next unit. Okay. So for that reason, we need to introduce in this chapter, in this unit, this concept of orbital diagrams. So for orbital diagrams, we use boxes and arrows. The boxes represent orbitals. Specifically, a single box represents one orbital. And each box has to be labeled somehow with that particular orbital. So you see, like for lithium, for my 1s box, for my 1s orbital, I have a 1s underneath it. If you have multiple orbitals that have the same notation, like for example the p's, there are 3 p orbitals, or in this case 3 2p orbitals. Even if a orbital is not being used, if one of them is being used, you need to draw all of them. So in this case, I put 2p under the 3 2p orbitals. So each box represents an orbital that needs to be labeled. Arrows are used to represent electrons, and each box, each orbital, can contain a maximum of 2 electrons, as we talked about before. Those electrons, if they are in the same orbital, have to have opposite spins, and we show that by arrows pointing in opposite directions. Usually we use half arrows to represent electrons. I am not going to be picky here, especially since I used an example here that uses full set that uses a full-headed arrow. Doesn't matter to me if you use a half-headed arrow, or whole-headed arrow. Just as long as you use an arrow and show the direction it is pointing to represent the spin. So those are the parts of an orbital diagram. The electron configuration is, you can use it to determine what electrons go in what particular orbital. So for example, with boron has the electron configuration of 1s2, 2s2, 2p1. So that means I'm going to have 2 electrons in a 1s orbital. I'm going to have 2 electrons in a 2s orbital and just 1 electron in a 2p orbital. I'm going to draw all 3 of them because I have a total of 3 2p electrons. But since there's only 1 electron, I'm just going to show 1 of them. Okay. So that's the nuts and bolts of drawing orbital diagrams. So let's go back to and then there's one other rule. What if you have electrons that need to go in orbitals that are degenerate, meaning they have the same energy? How do you place those? Like for example, with nitrogen. Nitrogen is has an electron configuration of 1s2, 2s2, 2p3. I've got 3 electrons that need to be placed in 2p orbitals. I know the answer is shown here, but how do I place them? Do I place them paired up first? How do I place them? What dictates how you place electrons in degenerate orbitals is Hund's rule, or also called the bus seat rule. It's called the bus seat rule because if you think about it, if you get on the bus, everyone wants their own seat to themselves, if possible, right? Same thing with electrons. If there are orbitals that are empty, that are available for an electron to sit in, go in, they will do that first. And only after the electrons, or only after the orbital is half filled, will they start to pair up. It has to do with electron repulsion that occurs when those electrons are paired in the same space, in the same orbital. They will pair up, but only when they're forced to, meaning only when there's no other free empty orbital available. So for nitrogen, when placing those 3 2p electrons, since I have 3 empty orbitals, each electron gets their own orbital. If I was to go ahead and do oxygen, which we'll do on the next slide, oxygen, that's 1s2, 2s2, 2p4. That fourth electron, there's no other 2p orbital, can't get its own seat, so it's going to have to pair up with that electron in the first 2p orbital. So when placing electrons into degenerate or orbitals of the same energy, half fill them first and then completely fill them, if necessary, with the appropriate number of electrons. So let's go ahead and do orbital diagrams for these 4. So helium is 1s2. These are the same elements we did in the previous video with regards to electron configuration. Helium only has 2 electrons, so both of them are going to sit in a 1s orbital with opposite spins due to Pauli exclusion principle. Oxygen. We said oxygen, it has 1s2, 2s2, 2p4, so that fourth electron is going to have to pair up with one other electron in a 2p orbital, but it's going to be of opposite spin. Sodium, we need to draw a few more boxes. Specifically, we need to make sure that all of our 2p's are filled, because remember, sodium is 2p6. And then we have one 3s electron that needs a home. So we end our orbital diagram with 3s and 1 electron. Last but not least, iron, which has 26 electrons. Its orbital diagram is long enough that it deserves its own slide, and I apologize that it's a little bit fuzzy, but I thought that would be better than my chicken scratch. But you can see here that for iron, we did boxes, designated the particular orbitals, making sure that electrons from those orbitals got paired in the appropriate box. Iron has its ending part of the electron configuration is 4s2, 3d6. So we've got 2 electrons in the 4s orbital. We put in 5 electrons for the 3ds. Remember, half filled first, 400. I've got 1 more electron. There's no more 3D orbital available, no more empty 3D boxes, so it's going to have to, that last electron will have to pair up with another. Now, when you draw your orbital diagram, at least in this example, I know the 4s gets filled before the 3D. So if you want to put this 4s electron box in between the 3p and the 3D, that's fine. If you want to put it after, that's fine as well. But just know that those 4s electrons, they get filled first before the 3D. So that is how you do orbital diagrams for elements. There are, again, more examples on your online worksheet. In the next few videos, we're going to talk about how we're going to expand upon those skills doing orbital diagrams for something called an abbreviated or noble gas electron configuration for elements.